Hi and hello everyone. After having seen the analysis of what one does with an MM1 queuing system, we will now move to our next queuing model that we consider, which is the MM-C queues, right. So, all the assumptions and everything is that we have made with respect to MM1 also holds true in the case of this MM-C model as well, except that the single server there in the MM1 now is replaced with C number of servers. They are all identical. There is no distinction between the servers that we make, and each server is having an IID exponential distributed service times is what they mean. I have not given the pictorial representation, but if you want, you can think that there is an arrival which happens with the Python process, right. Now there are C servers, so each one of them, there are C of them, so the customer can go either here or here and they can exit with a Python process rate lambda, right. So that is what would be the case. So there are C servers is what then you will have here. So this is the pictorial representation. If you wanted to see, the single server one is replaced now with C servers, each of them having an exponentially distributed service time with parameter mu. Okay. Now since this is also like exactly like this MM1 queue, this queue can also be modeled by a birth-death process, because at any point of time the state space is going to change only by one, either by an arrival or by a departure, right. Since the time is continuous, right, simultaneous departure, the probability is 0, right. That is how things are, the time is spanned out in a way, right. So this can be modeled as a birth-death process with rate, since arrivals happen one at a time according to a Poisson process. So there is no dependency, it does not depend on the number of customers in the state. So the arrival rate would remain as lambda for all states like in MM1 queue. But now since there are C servers here, so the service rate or the depth, the rates we have to determine. Now if you look at when there are C servers, suppose if there are n customers, right, where n is less than or equal to C, then what happens? Suppose assume that n is less than or equal to C, then there are n customers are there, right. So that means that what? That suppose if there are, say, n is 10, right, and C is 20, so then there are only 10 servers who are giving service to the customers, right. The remaining 10 servers are idle. So now what is the rate of departure now? Because 10 servers are working independent of each other. Now what is that you are looking at? A departure will happen according to what? If you look at little closely, like you will see that out of these 10 servers who are giving service currently, any one of them can finish the service. So when any one of them finishes the service, then there is a departure happens. So what is the rate of departure? Then the time that you have for these 10 servers, the minimum of these 10 servers, service times, right, service time distributions. Each one of them is exponential, so the minimum is also exponential. So the minimum time that will be required for a departure to happen would be 10 times mu, right. When n is less than or equal to C, right, this will be n mu. That is what we have. Now when n is more than C, that means all the servers are busy and the departure would happen according to an exponential distribution with parameter C mu, because any one of these C customers can complete their service earlier. So the minimum time that is required would be exponential again with parameter C mu. So again, this you see here, the minimum of this exponential thing is what we are using it to determine what are the rates for it. So this is then the rates for a departure from the system. So that is what this will be the death rate for this BDP, which is we are trying to model using this BDP for this MMC queue. Okay, so the transition rate diagram, then you can draw it as if here there is 0 number of customer in the in the system. So the arrivals at each state can happen with respect to rate lambda only. So everywhere this is lambda. But whereas the service rate, right, the service rate would be that when there is only one customer in the system and there are C server in the system. So this the service departure would happen at the rate mu. When there are 2 customer in the system, the departure will happen at 2 mu. When there is 3 in the system, the departure would happen at 3 mu. When there is C in the system, exactly the departure rate would start is at the rate of C mu. When it is C plus 1, since there are only C servers, right, 1 will be there in the queue, the remaining C would be there in the service. So the rate at which this departure can happen is C mu, and hereafter everything is, all the rates are C mu. So now if you look at this point onwards, so this portion of the transition rate diagram, if you look at it, what you are seeing is it's as if it's like an MM1 queue, right, but with rate instead of lambda and mu and lambda and C mu is what then you are looking at it, right. So in addition to this, now we have on the, this portion is extra here, right. So that's what you are seeing it here, right. So this is what analysis also it will come out to be in that way only, right. So this is the rate, birth and death rates to model this MMCQ through a BDP, right. Now once we have this birth and death rates, then our objective is to obtain the steady state distribution for the number of customers in the system at equilibrium, right. So we have already developed the theory, which is basically the iterative method in terms of lambda naught, lambda 1, and you just substitute this particular lambda n's and mu n's as given here into that expression to get this expression for p n's, which is in terms of p naught, right. This was a product of the ratio of lambdas and mu's, right. That is what you had it, and when n is less than c, you have the death rate was the mu n's were n mu. When n is greater than c, you will have this mu n's or c mu, right. That is what you had it, right. So because of this, you have now these 2 expressions for n lies between 0 and c, and c and more you will have these expressions. So this is something like a Poisson that is happening, and this is something like an exponential term, that is what is happening here, right. So lambda by c is what then you will get. So this is my Pn by substituting the lambda n's and mu n's into that expression, right. But if you want to try to solve this through alternate other methods, you are most welcome to do, but we will just take one method and we will go ahead with getting the solution. Now to find P naught, how do we find P naught? Then you have to use the normalization condition, which is summation Pn equal to 1, which will give me P naught to be that sum of these terms from 0 to c and 0 to c minus 1, and sum of these terms from c onwards, right. So you will have this term, right, and you will have this term, right. That is what will give you my P naught. Now lambda by mu, right, we call it this as the offered load to the system. So this is the offered load to the system, which is what is denoted by this R, and R by C is basically the offered load per server or traffic intensity. So this is what is the traffic intensity. So lambda by mu would be this offered load R, and R by C, which is equal to, we call rho, is basically lambda by C mu is the traffic intensity. So now this lambda by mu, I can plug it as R to get this expression, right. Now again this expression here, I can this summation if you look at it now, this is what is the infinite geometric series it will come. So this c factorial I can take it out, c to the power n minus c. So R c, if I take it out, I will get this as the outside term. The inside one will be summation n is equal to c to infinity R by c times to the power n minus c, which is a geometric series which will give me this expression, and hence this is the expression for P naught, where this series would be convergent for rho less than 1. So rho is R by c. It's intuitive, right. So the lambda must be less than c mu. So the arrival rate must be smaller than the maximum possible rate of service, which is C mu here, right. So, that is what is the stability condition, and that is what will be the condition for equilibrium in MMCQ. So, here what we are using is this term, which is equal to this, and this is what we are getting it here, that is what we are seeing it. So, this is P naught and this is Pns. Now, we have obtained the solution of the steady state probabilities. Now, what we can do? We can do for try to obtain the performance measures. So, the first one that we will consider is this quantity of LQ, which are this here, it is easier rather than obtaining L first. LQ is easier because of then you will need to deal with only one summation, right. So, in any model like this judgment you have to make, like which quantity you will tackle out of this 4 primary quantities that you have L, LQ, W, WQ. So, accordingly like you handle that and then get one and then you can get the remaining 3, right. So, in this particular case, because of the nature that we observe here, like 2 different terms, at least these terms will be in some way unique, there are 2 different sums are involved. So, obviously like you would want to tackle only this part of thing only will be relevant if you take LQ first, that is the idea. So, LQ is essentially the same, like we can relate to Pn in this manner, right. For n C plus 1 up to n, if there are C customers, at most there are C customers in the system, mean there will be no Q, right, there will be no Q. So, the Q size will be 0, the Q size will be positive only if there are more than C or at least C plus 1 customers in the system. That is why the summation is basically C plus 1 to infinity n minus C, right, times this Pn. So, the Q size will be n minus C when there are n in the system, right, where my n run from C plus 1. So, the minimum value is 1 for P C plus 1, right. For P C plus 2, this will be 2, right, that is the Q size, that is all. So, once you write down this expression correctly, then you just have to substitute this Pns. So, in this case the Pns would be given by the second term only, right. We want to, that is the reason why we want to pick up such kind of things. So, this is what you have it here. Now, again here you do some algebraic manipulation, there is nothing much here. So, you take out one n minus 1 C outside. So, RC will come, P naught is there here, and this side C factorial is there, C minus 1 is there, right, C to the power n minus 1 rather, right. So, this one, the one row also you take it out, then you can write this as n minus C, this is R by C. So, R by C, so this is basically rho to the power n minus rho n minus C minus 1 is what then you will get from this one. Now, once you get this is earlier we have seen that summation some m times rho to the power m minus 1, this summation we know already to be equal to this, which we have seen in MM1 case itself. So, that gives me my LQ to be this expression, right. So, R rho C factorial 1 minus rho square P naught everything is in terms of P naught, fine, but still P naught has an explicit expression as given here, which is a finite quantity, a simple quantity. So, that is what is the expression for LQ, right. Now, once I know LQ, then I can employ Little's formula to get WQ, okay, WQ as LQ by lambda. So, I will get only this, right. 1 rho is lambda by C mu, lambda will get cancelled. So, 1 C mu will come here, right, that will be my WQ, and once I know WQ, then 1 by mu times plus WQ will give me the W, right, and finally employs Little's formula again to get from W L, right. So, which will give you this expression. So, these are once you obtain one expression, then these are straightforward expressions. Note that this can be obtained directly L and LQ. From LQ also you can obtain L directly through this relationship, which is applicable for any GGC systems, right, which we have seen earlier itself. Okay. Now, again if you want to see as a parameter of rho how this behaves, as a parameter of C how it behaves, you can analyze the quantities of interest depending upon your requirement. Okay. So, those things you can do. Now, similar to that, like we know the FTQ0, which is probability of a customer has 0 delay in queue before receiving service, and 1 minus of that is a customer has a non-zero delay in queue before receiving service. This will be the probability of queuing, that if a particular customer has to arrive at a particular point of time, then what is the probability that you are expecting him to be waiting for service rather than getting into the service immediately direct, right. So, that is what will give you this. So, now as in the case of MM1, this FTQ0, which will correspond to 0 delay, when this will happen? This will happen when there are at most C minus 1 in the system, right. If there is C in the system, then you know that all the servers are busy and anyone arriving at that point of time has to wait. So, the wait is 0 if the number of customers in the system is less than or equal to C minus 1, that is what we have here, n less than or equal to C minus 1. This in system is redundant, but of course, this is what it is, right. So, that means this is probability of 0 to C minus 1 of Pn. Now, again only one expression for Pn would hold. So, that is this expression will give you this, right. Now, we want to evaluate this like in a more compact form. So, you can see that P naught expression from here, you can think that P naught, so our 1 by P naught is equal to this expression, and out of which we want this expression. So, 1 by P naught minus this is what will give you this expression, right. 1 by P naught minus this expression is what this particular sum. So, instead of this sum I can replace with this. So, that is what you will get here, right. So, multiplied by P naught. So, here it is 1 minus r to the power C P naught times this quantity is what then you will see here, right. So, this is the probability of 0 delay. So, once you obtain this, then the probability that a customer has a non-zero delay in queue, which means an arriving customer has to wait for service. What is its probability? That is 1 minus FTQ of 0, which is given by this quantity, right, which is given by this quantity, which is essentially this quantity where P naught explicitly written down here. And otherwise, if you look at this RC P naught divided by C factorial, if you think, right, this is what is PC, that probability of finding C customers in C in the system in MMC model. So, some books and sometimes like we will also write this in terms of PC. So, you can write this PC. So, this whole thing, this expression, whatever I have circled here, this expression can be written down as PC by 1 minus rho, because except this 1 minus rho, remaining terms is what is given by the probability that you can find C in the system in changing equilibrium, right. So, you can also write in this form. Now, this expression, right, this expression is what is given representation C of CR and is called as Erlang C formula or the Erlang second formula or the Erlang delay formula. All three are mean one and the same as far as we are concerned. We will use any of these three interchangeably. Erlang C formula or Erlang second formula, Erlang delay formula makes much more sense directly when we use this, because what is the meaning that what is the probability of delay or Erlang delay probability, sometimes that is also it is being referred to this. So, why this is? Because this is one which has been found by Erlang himself and used till today, because in a multi-server system, if you want to compute what is the probability of delay, what is the probability that an arriving customer has to wait, then what you employ is Erlang C formula or Erlang delay formula. So, this is what is Erlang delay formula. It is very, very important. As we said that when Erlang did the analysis, he found that MMC model fits well into the situation. Multi-server, Markovian arrival or Poisson process arrival and exponential service time model fits well in most situations, and that is true till today. In most of the communication systems, when you want to do the analysis, what you will use is this Erlang's delay formula to get that in the multi-server situation. So, that is what is the relevance even today, and this is what is being used, and that is why it is called as an important one called Erlang delay formula in this case, which is basically the probability of delay in a multi-server system. that is what it is. Okay. So, this is an important quantity as we said. So, that is what this quantity is. Now, let us look at slightly more little bit deeper into this Erlang C. There is much more you can do, but we will just hint a little bit on that. So, this is a measure of congestion. Okay. So, many a times the quality of service, right, has to be specified in terms of certain parameters or certain requirements that you pose. So, the requirement in a particular situation, right, say for example, in a call center. Imagine a call center situation where there are multiple agents, they are working on it, right, they are working on it, and the calls arrive. Calls arrive according to Python process. Each agent will take an exponential amount of time to serve one particular customer, right, and there are multiple agents, right. So, now for this, if you want to design a system, if you want to design a call center, if your requirement is that if you want to bound the probability of delay for an incoming call, it means incoming call has to wait. So, right. So, if you want to, so this basically like that depends on the congestion that you experience on that call center network at that point of time. So, you want to do that analysis. So, this Erlang C formula is what is a measure of congestion used in that situation. Okay. So, this gives the probability that a customer is not able to immediately access a server. So, in a call center situation, you are not able to talk to the agent immediately. You are put on the wait, and some music is played or some announcement is made. These are all other things that is going on, but you are waiting essentially, right. So, as a simple example, assume that for a call center, the MMC model is applicable, which means that you have made some analysis and then which tells you that this model is applicable. Okay, that is all. What are the rates? The rates is 30, everything is by hour that we will take it. So, that means that this rate is 30. So, per hour 30 calls come, and mu is equal to 12. So, which means each call will take an approximate about on an average 5 minutes. So, that means there are 12 calls you can attend in a 1 hour by one server, and there are C servers. So, there are C call center employees are there who answers the call. So, there are C servers are there. So, this will give you my R is 2.5 and hence rho is 5 by 6, rho is still very high. So, from the Erlang C formula, we can compute this CCR, which is the basically probability of delay to be equal to this. So, that means the probability of no delay, right, this is what the probability of delay. So, the probability of no delay will be 0.298. So, it is 0.3 if roughly you can say. Okay. That means that what 70% of the people have to wait and only 30% of the people get into the service, or they are able to connect to the agent immediately when they are making a call. So, now the question is it desirable? Do not know, it depends on situation. Suppose if you wish that not more than 10% of the callers experience positively. So, that means that you want to bound this quantity to be 0.1. Then what you do, right? In crude way, of course, there are efficient ways of doing. One crude way is you look at this CCR as a function of C and keep on increasing C such that this becomes less than 0.1, and right, that is what you want it, and you will achieve that with at least the value of C is equal to C. So, minimum C such that this is satisfied is what we would do, but of course, there may be other ways of doing it, but this is one way easily one can analyze with number of servers, because it is not very complex situation and one can do this easily. So, this C will be 6, you need 6 servers or 6 agents you need in order that this is true. So, this is what is we call it as a quality of service parameter. So, then you can say that the quality of service parameter here is a measure of congestion that not more than 10% of the callers will experience delays when connecting to the agents, right. So, now for which how many C you need is this what it is, you can see. So, this helps in the analysis of deciding the number of servers, and this is a typical example of problem of determining an appropriate number of servers according to some criteria. So, this is again a large class of analysis that one can do with respect to this determining the appropriate and in what sense. So, you have to determine under what is the criteria that you are looking at it. So, according to that, you know, you will. So, one approach is basically choosing C according to a measure of congestion. So, in this case we can take Erlang C formula itself, right, much like for example this kind of this kind of situation that you have it in mind, and such an approach is referred to in the literature as QED regime or quality and efficiency domain. So, you are determining in such a way that the measure of congestion, which is probability of delay, for example in this case is bounded by this. These are requirements from the regulator's point of view, that you know, if you want to be that you are specifying that, you know, I need a call center to be set up with these parameters, with this quality of service. So, you need to monitor and you need to take action if that is not meeting, right. So, how do? You have to do all this analysis. So, this regime is what is not QED regime. QED is so common in this area to tell about this, what is this. So, under this, see, an approximate formula is basically R, which is the offered load, plus some beta times square root of R, right, where this beta is connected to the CCR. Suppose if this quantity is, if I call it alpha, there is a formula that connects alpha and beta. So, this is a constant which is connected to that R. Okay. So, what this tells roughly is that, forgetting about this beta, you see if R is your offered load, right. So, here R is say 2.5, say for example. Now, if you want this square root of R, so you add additional square root of R server along with multiplication with some beta to get to be under this domain. So, this is what often called square root rule, or in the call center thing, that how many staffs you need is essentially square root staffing rule. So, determining the number of servers. Determining number of servers is important in many contexts. So, even in this case, when there are call taxis are there, like these kind of situations where how many drivers you need or how many cars you need, depending upon what is your server in this particular case. So, all these things would require this kind of ideas. Of course, there are much more sophisticated rules are there, but this is one very simple rule, which is approximation, which works quite good in different situations. That is what you would see, right. So, this is what is the square root. So, this kind of things is the Erlang C formula helps us to get immediately certain managerial insights as to what to do to improve the system, right. Now, having done that FTQ0 or 1 minus FTQ0, right. Now, let us look at the delay time distribution. Delay time distribution here is basically like similar to the analysis of MM1. We determined the probability distribution of the waiting times TQ assuming FCFS and using pasta property, right. TQ equal to 0 with certain probability that you already determined, and for TQ greater than 0, right. So, that means for T strictly greater than 0, right. For small t strictly greater than 0, if I want what is the distribution CDF of this TQ, then that is given by FTQ. Now, this sum exactly same, but now since there are C servers, so things will be of this nature, right. So, if you found the Pn is the probability that an arrival finds n in the system, of course, this is an, but because of pasta property this is equal to Pn here, right. So, this Pn, and if an arrival finds n in the system, how many service completion has to happen before time t, so that he gets out of the queue to get into the service by time t, right. Since there are C servers, right, when there is more than C only, all the C servers occupied only, like he will queue, right. That is the time you will get this t strictly greater than 0. So, that means all the C servers are busy. So, that means how many service completion has to happen? That n minus C plus 1 service completions has to happen, so that he gets into the service with any one of the server, right. So, where my n is ranging from C to infinity. So, this is what is the case. Now, once you written down this, then it is mechanical calculations from now onwards. Now, when n equal to greater than or equal to C, so the system output is Poisson with rate C mu, right. The death rate is C mu is what you are doing. So, the distribution of n minus C plus 1 service completions is gamma, right, because gamma is what you know. So, that means that now I can write it down, FTQ of t is equal to this quantity which is already we have, plus Pn is basically P naught times. So, this n is equal to C to infinity. So, only the second expression is valid, P naught times R to the power n by C to the power n minus C times C factorial. This quantity and this P naught is together with this Pn. Now, what is this? This is n minus C plus 1 service completions, where the with C mu is the output rate and this many service completions should happen. So, that is what you have here as written down as a gamma random variables CDF 0 to t of appropriate parameters n minus C plus 1 and C mu is the rate, right. So, that is what you will see here as the gamma CDF here that you have written down. Now, once you write that, now you interchange, assuming that is possible, that this integral and this sum you are interchanging. See, whenever we do such kind of operations, we will always nicely assume that these are possible, right. These are the conditions. If there are any interchange of differential with respect to sum, with respect to limit, with respect to integral, everything we will assume that they are all satisfied. So, we do encounter in this course only that kind of quantities. So, hence there should be no problem. So, if you take this summation inside and leave out certain things outside, say for example, you will take 1 r to the power c out and p naught by c minus 1 factorial. So, this is what then you will get here, right, 1 c minus r multiplied and divided by this, you will get this here. So, that is what you will get here. So, there is only mu here, there is no c mu business. So, this quantity, like this sum you can solve it here, right, to arrive at this expression along with this one is what then you will get here, right. So, c mu c x is already here, mu r x is what you will get from here is what this quantity is. So, now this one if you look at it again, this quantity is something like an exponential, right, an exponential one. So, that is if you solve. So, this quantity is you will get it to be this, right. Now, FTQ if you substitute from the earlier one, then you will get this as the expression for the line delay distribution or the distribution of waiting in the queue for an MMC system is given by these expressions, right. This calculation you can try it once. Now, from this CDF, if I want what is the probability that TQ greater than T, which is 1 minus, so this is wrong, okay. So, this is basically F TQ of T. So, this is basically 1 minus F of T is what this quantity is, okay. So, this is what is the quantity that you have here, and this is equal to this expression. There is nothing but 1 minus of this. So, that means this expression is what this is there. So, this is the probability that the weight exceeds T time units. If I want, then this is the expression that I have, and therefore, if you condition on the fact that you have to wait, then you can obtain it as to be this quantity, which is now purely an exponential distribution. So, now this is what is quantities that you can obtain, right. Probability if you have to wait, given that you have to wait, what is the probability that the weight will exceed T time units is purely an exponential distribution is what then you will arrive at here. That is what this means here, right here, that is what it gets here, because this is probability of no weight and this is probability of weight, and this gives me this expression is what is this one, right. So, we can now again verify the what we have obtained earlier through Little's formula, that from this distribution that you arrive at this expression, which is very simple. You can also try it here, right. Now, the other one is that Sojourn time distribution, that what we want to find a formulas for the CDF of the waiting time T in the MMC system. So, this is unlike MM1, it is not that straightforward like what you have handled in the TQ and to T to transfer the result. It is not that straightforward, but you just have to be a little bit more careful, that is all. So, in this particular case, there are two possibilities are there. One, customers having no weight in the queue. So, that will happen with probability FTQ of 0, right. In this particular case, the sojourn time or the system time will be is simply time in service, which is exponential with parameter mu. This is one group of customers. When they don't have to wait when they arrive to the queue, right? That is what is this system time. Now, in the other group of customers are that they have a positive wait in the queue. So, this can occur with probability this, and in this case the time in the system or the system time or sojourn time is wait in the queue, right. Wait in the queue means you are made to wait in the queue given that you have a positive wait, right. That is what is that wait in the queue plus his time in the service. So, this we have already seen to be exponential C mu minus lambda, and time in service is again exponential mu. So, this is what we have to do. So, in this particular case you have to obtain this as a sum of two exponential random variables, for which we have already seen an expression when we talked about properties of exponential distribution. If you have two independent exponential distributed random variables with different parameters, this is not IID. IID case is simple, it becomes gamma, but this is not IID. This is two independent but with different parameters. Then the sum is given by the convolution of these two densities, which will turn out to be this expression. We have given it in that particular form as hypo-exponential, like you can go and check with that. That is what is the case here. Or if you want to write in terms of transforms for such quantities, you can simply take the transform of lambda 1, which is lambda, say Laplace transform. So, lambda 1 by s plus lambda 1, and this is lambda 2 by s plus lambda 2. The Laplace transform of x1 plus x2 is simply the product of these two Laplace transforms, right. So, that is very easier to understand and see. So, this sum nevertheless is given by this expression here, which is what is the density, right. So, how one can handle, you can recall which we needed to obtain this sum. So, this is one exponential with one parameter, this is another exponential with different parameter, right. So, to obtain this is in the second class now, right. If you do the required CDF for the second class of customers, that you have to wait for the second class of customers. So, this is basically given that you have to wait, right. So, this means that for the second class of customers, right, with the positive wait. So, that means that this is basically given that you have to wait. So, wait in the queue, right. That is what wait in the queue, which is occurring with wait in the queue, which is occurring with this probability is what we are seeing. Customers with positive wait in the queue, which means you have to wait, then only this thing happens, right. So, that will be right. If I simply employ this formula, lambda 1 lambda 2 by lambda 1 minus lambda 2 is that lambda 1 lambda 2 by lambda 1 minus lambda 2 the distribution function if I take it. So, it will be something like this is lambda 1 by lambda 1 minus lambda 2, lambda 1 by lambda 1 minus lambda 2, this is the other one. So, this is you can write it in this form as a difference of between two exponential functions with appropriate coefficients is what then you will get. Now, this one is for the second class. Now, putting together this is what you will arrive at. So, for the whole F system, MMC system, if I want to look at the system time or sojourn time, this will be an exponential with parameter mu with this probability and this distribution, right, which is what is given by here with this probability is what then you will get here, right. Now, you just plug it here, you just plug it this quantity and this. So, you already plugged in here. Now, you just simplify it, you will arrive at this expression as the sojourn time expression, which is not a nice form as in MM1, but still nevertheless you will be able to obtain it using your usual processes that you have followed here, right. So, there could be some other quantities are also of interest with MMC, does not matter, but as we might require. These are certain fundamental performance measures that you obtain it for the MMC model here. Okay. Now, let us take an example and see like what kind of some kind of questions that can arise in the case of an MMC model. So, let us take a hospital system which is modeled through an MMC system, assuming that MMC is applicable there, which means that all the assumptions are satisfied here, at least approximately, right. With lambda equal to 6, which means there are 6 patients come to the hospital every hour, mu is equal to 3. So, 3 patients are getting served, which means each patient is getting taking about 20 minutes, and there are 3 doctors is what then you have. So, the hospital authority are interested in knowing the average number of patients waiting, right. So, LQ, the average amount of time a patient spends in the hospital overall, which is W. So, the average percentage of idle time for each of these doctors or any of these doctors, which is given by 1 minus rho. So, these are some quantities. There may be other quantities also which may be of interest to you. Now, if you look at here, from the data we see that R is equal to 2, so and hence rho is equal to 2 by 3, and hence P naught is computed to be 1 by 9, right. Now, from this quantity we can use our expression for LQ to compute LQ to be 8 by 9. So, the average number of patients waiting is essentially 8 by 9, and W is average time, that average amount of time a patient spends in the hospital is basically this much time, right. 1 by mu times plus LQ by lambda, which is 13 by 27, which is roughly about 29 minutes is what he spends. Then the long term average fraction of idle time for any server is equals 1 minus rho, so which is 1 by 3. So, given that there are 3 doctors on duty, 2 of them will be busy at any time on average, since R is equal to 2, right. So, that is what is the offered load. So, 1 doctor will be free almost at any given point of time on an average, right. So, that is what this 1 by 3 will turn out to be, the average fraction of idle time for any server. Now, additionally, suppose if you are looking at these kind of questions, the fraction of time that there is at least one idle doctor, right. If there is at least one idle doctor, there are 3 servers. So, this is a 3 server model, or 3 doctor is what is there. So, you want at least one doctor to be free, right. So, this must be sum of P naught plus P1 plus P, sorry, this is P2, it is not P3. So, this is P2, right. So, this will be the same as P of TQ equal to 0, which is 5 by 3, you can compute. Suppose if you want at least 2 doctors to be free, at least one doctor free, then all these things you can compute it from this distribution, from the stationary system size distributions that you can do. So, again you see that there may be some question, there may be some more question with respect to this, but if that can be answered through whatever we have obtained, we can do. But if there are some other thing that is you want, suppose if you want to know that what is the duration of the time the servers are busy, all servers are busy, but at least one servers are busy, then you need some more analysis, some more measure that you obtain, which is again it is not very simple one, they are all very little complex ones that you obtain. So, these are the very basic ones is what then we are dealing with it, and this is what is the analysis of MMC model. As you see, it mirrors most of the time MM1 models with additional features like C servers. So, that the question is number of C servers we can determine, and certain performance measures that you try to get with respect to the additional features that is there inside these models. So, we will continue our discussion on this BDP, different kind of BDP models as we go further, at least some more models also we will deal with it, right. So, here we end the discussion on MMC, we will see with the another model in the next lecture. Okay. Thank you, bye.